So as I said, I'm going to be talking about recurrent neural networks, which in machine learning timescales are ancient history. But we're going to talk about some of the features of recurrent neural networks that make them useful for doing large-scale simulations. So these are based on two works, which can be found on arXiv. They'll be in PRB soon. I worked with some really great people, most of which were in Waterloo at some point. So to start, I'll talk about the model that we focus on, which is the antiferromagnetic Heisenberg model. It's defined with nearest neighbor couplings only. And for the square and triangular lattice, it has a Néel-ordered ground state. So the quantum fluctuations in the model don't destroy this ordering in the thermodynamic limit. But the model itself is SU2 symmetric. And so this Néel order in the ground state implies that this SU2 symmetry is spontaneously broken. And this spontaneous symmetry breaking is well described by Anderson's Tower of States. So I won't talk about the Tower of States in detail today, but it does play a role in how we interpret some of our results. So if you want to chat about it, I have a poster as well. So for the square lattice, an important detail is that we have the Marshall-Peierls sign rule, and so we can make this Hamiltonian stochastic, and the wave function will be sign-free. However, for the triangular lattice, there is no known local unitary that will do the same thing, so the ground state will have a non-trivial sign structure. There's one important thing to highlight is for other lattices, such as the Kagame lattice, there is actually enough frustration to destroy this Néel order, so I'll maybe talk about that at the very end. So I got a nice introduction from Adam, so I'll zoom through this, but I'm essentially using a neural quantum state to represent, to parameterize our ground state wave function. The idea is that we have sort of a compressed representation of this very large wave function, and we're minimizing the variational energy. The specific wave function that we're using is a recurrent neural network. And this is sort of a schematic of what it looks like. I won't go into all the details, but the main points I want to highlight are this is the structure of the network. You can see that there is essentially a one-to-one mapping between these green boxes and the lattices, the spins on our lattice. So this has nice malleable structural properties that we can sort of bake in to our network. But the most important thing is that you can see in these green boxes, there are these W's, and those are the trainable weights of our network. And every single recurrent cell has the same W in them, and that's this recurrent property that we're going to take advantage of. So what do I mean by leveraging recurrence? So if we look at this picture and we say that all of these green boxes are the same, when we do a forward pass of our network, we can think of it as applying the same nonlinearity, which is this F sub W, in times, where n is the number of spins in our lattice. And that's our recursion relation that sort of defines this RNN, and this gives us a number of parameters that's independent of the number of spins in our system. And so that's really the crucial thing that we are taking advantage of in all of our simulations. This feature of the network allows us to do what's called iterative retraining. Iterative retraining is a transfer learning technique where you're transfer learning across system size. So what we can do is we train a network for a somewhat small lattice, like a 6x6 lattice, and we optimize the parameters with variational Monte Carlo. And because the number of parameters is independent of the number of spins, we can then use those weights as the initial weights for our larger simulation. So I'll show you what this looks like. We start by training our network for, as I said, a 6x6, and we maybe do a long number of training steps. So this is similar to what Adam said. We want to put the most amount of effort into training on small system sizes because the compute grows very quickly with physical system size. So then we will reuse those weights for the next larger system size, and we can keep doing this over and over again until we get to a very large system size. So for this square lattice, we end up at a 32 by 32 lattice, which is very big for neural quantum states.
Question?
It's a 15-minute talk. Can we wait until the end?
Sure.
Thanks. So yeah, as I said, we're reducing the number of training steps all the way until as we get to larger and larger lattices to sort of control the amount of compute so that our compute doesn't scale quite so badly with system size. And we do this with a predefined schedule that we introduce, and so we're able to tune the amount of training that we use, and also that translates into the accuracy of our simulations. So these are all of the different schedules that we look at, how we reduce the number of steps as a function of system size. And the main point to take from this figure is that the darker colors are longer training time. And you'll see this show up in the accuracy of our results. So I'll first show the results for our square lattice simulations where we benchmark against quantum Monte Carlo. And then I have results as well for the triangular lattice. So the first thing to look at is the variational energy. And these are all of the finite size energies that we obtain with all of our simulations. And so you can see that as the training time increases, so the color gets darker, our energies systematically improve, converging towards these quantum Monte Carlo reference values. And because we have a set of systematically improving wave functions, we can do a zero variance extrapolation, and this gives us estimates for the finite size energies that are in really, really close agreement with the quantum Monte Carlo. So you can see even all the way up to our 32 by 32 energies, they're in really good agreement. And then using these zero variance energies, we perform the finite size scaling and extrapolate to the thermodynamic limit to get an estimate of the energy that's, again, in good agreement with the quantum Monte Carlo. But the energy isn't everything, so we look at the sublattice magnetization, which is the order parameter for the ordered state. And there's a lot going on here, so I'll just point out a couple of things. We calculate the sublattice magnetization with two conventions. That's going to be the two different colors. And the solid markers are computed with the full 2-point correlations. And the open markers are computed with the Z component only. And for the Heisenberg model, the finite size ground states should be SU2 symmetric. So these two estimates should be the same. And so obviously they're not the same, which is indicating that our network breaks this SU2 symmetry. We're not learning this full SU2 invariance for during our simulations. But I'll click through and you'll see the colors getting darker. So more and more training, more and more accuracy. You'll see that our full 2-point correlation estimates converge onto the QMC values. And you'll also see that this SU2 symmetry, at least for some lattice sizes, gets restored. So you can see that the open markers are getting closer to the full filled markers. That's this SU2 symmetry restoration. And you can see that our estimates of the sublattice magnetization are getting closer to the estimates from quantum Monte Carlo. And you can see that our two estimates are in agreement with each other and with the QMC in the thermodynamic limit. Okay, so now for the triangular lattice, we don't have careful finite size reference values, but we do have reference values for the thermodynamic limit. So here, again, we have darker color is more training time, and we can again see this systematic improvement in our finite size energies, but also in the extrapolations of those energies. But when we do our zero variance extrapolation, we're able to get estimates for the finite size energy that actually extrapolate to a value that's very, very close to the best variational energy, which is this IPEPS reference here. So this is really exciting. And then when we look at the sublattice magnetization, we can again see that our two methods for computing the sublattice magnetization, they're in agreement with each other. They are in agreement with the tensor network methods. However, for any discrepancy, it could be related to our method, it could be related to the tensor network method itself. So the discrepancy here is maybe less of an issue than it would have been for the comparison with quantum Monte Carlo. But we also still see this SU2 symmetry breaking. And here, we actually didn't see it get restored as much as we did for the square lattice. So, oh, and I just have a picture here of the structure factor in reciprocal space, just to show that we are capturing this. There is some noise in the intermediate space, but we do really see the peaks in the structure factor at the desired locations. So just to conclude, we're using RNNs and we're training them using iterative retraining to get to very large lattice sizes. And this is a powerful method for reaching large system sizes. We've already heard that training very large networks from scratch can become really unstable. It can take a really, really long time just because the energy calculation, which happens at every step, is very expensive. And maybe you need more of those optimization steps if you're starting from scratch. So iterative retraining and RNN wave functions are powerful for that reason. And also obtaining accurate large system size results is ultimately what allows us to do this finite size scaling, which is one of the central tasks in condensed matter theory. So I think this is really establishing RNNs as a powerful tool for doing this kind of study. Two things that I didn't talk about today are how we used Anderson's Tower of States to theoretically support our results, but if you want to chat with me, I'd be happy to. And then also, I'll just say that even though our results for the triangular lattice are very good, the simulations were much more difficult than the square lattice. And there are lots of reasons for that, so I would be happy to chat more. And then I think in the outlook, it will be very interesting to see what happens for a disordered state. And yeah, what happens to our simulations? They will become much harder, but how and what can we get with our methods? So that's all.
Thanks for the talk. I just had one question about the architecture. So should I be interpreting the schematic as an unraveled recurrent neural network? Are you in other words, are you interpreting the time of the recurrent neural network dynamics as another spatial direction in my system?
Yeah, so the time index is a space index for us.
I see.
Exactly.
Yeah, thank you.
And I guess for the unraveling piece, you could in principle make each of these recurrent cells have different spatially dependent weights. And that's been used for things like spin glasses and stuff. But if you share your weights in this way, then you get the recursion.
I see. So are you basically only allowed to look at 2D systems or?
I mean, you could share in 3 dimensions
unravel,
as well.
Just whatever the last dimension is.
Yeah,
okay.
Exactly.
Okay, thank you.
Thank you. Very nice talk. So one thing I'm wondering is you mentioned that you can extrapolate the thermodynamic limit, but I guess the sense is slightly different to, for instance, if one was using IPEPS or IDMRG, because there you can actually take the wave function, evaluate the observables. Is it what you mean in here that you can also do the same thing in here, or it's just about the energy estimate and telling you how far off you're potentially away from the the thermodynamic limit value?
So we extrapolate to the thermodynamic limit through the finite size scaling, and then we're comparing to these reference benchmarks that do work directly in the thermodynamic limit. So this IPEPS result, they actually did gradient optimization of an infinite PEPS. So that's a strict variational bound on the energy directly in the thermodynamic limit. So it's great that we're able to get so close to that energy because that's sort of the closest thing to working directly in the thermodynamic limit. I don't know if that answers your question, but I guess, yep.
So I guess like this is about evaluating the energy and checking how close we are compared to this like thermodynamic value, but not really to evaluate observables in a thermodynamic limit with this method. Is that correct?
Right. All of the simulations are finite sized. And yeah, I think the strong part is getting to large enough systems where we can reliably do this scaling.
Thank you for the nice talk. You highlight that the number of parameters is independent of the lattice size. Is this expected that this will give you continue to give you accurate result as the system size further increases?
Yeah, that's a great question. So no, you essentially choose a number of parameters that will be sufficiently, in theory, the number of parameters should scale with the system size. So this is sort of an explicit technical statement. And yeah, you can imagine doing some sort of scaling where you just reduce and reduce and reduce the number of parameters until it breaks at some system size. Yeah.
Very nice talk, Schuyler. Two questions, one quick and the other one I'm sure is more for an extended discussion. So you mentioned symmetries, right? Mm-hmm. So full SU2 was not imposed, but I guess total SZ equals 0 was imposed?
Yes.
And that's the only symmetry? Which were the symmetries?
So we explicitly imposed the SZ equals 0, and we do this sort of lattice symmetry augmentation as a sort of fine-tuning step in the training, but it's not explicit.
Okay. Now the tougher question, what's your view on why the triangular lattice is more difficult? Is it because there are many computing states? Or?
Yeah, so I mean, there are a couple of things. I think the most obvious culprit would be that there's a sign structure, and learning the sign structure is maybe hard, or maybe that doesn't generalize as well in system size and something like that. But another subtler point is that we're looking at lattices that are commensurate with the ordering. And so for the triangular lattice, you have to have lattice lengths that are a multiple of 3. And so then we're also able to, we have to take really big steps in lattice size.
So the transferability is more problematic.
Mm-hmm. Yeah, so taking bigger steps in this transfer learning can also maybe be a problem.
Okay, so probably we can continue the lecture offline. Let's thank the speaker again.